Welcome to part 5 of video series on relational databases, Informal Introduction. In this part, we will be talking about fitting various hierarchical and graph structures into database table. Let's talk about implemented hierarchical data structure. Previously, we already seen one example of hierarchical structure. That was when we were considering customers, orders, and order items. But that hierarchical structure was pretty simple because it was well defined. There were only 3 levels, and these levels were known. So first level was customer, second level was order, and the third order was order item. Now, what about hierarchical structure which is currently shown on the screen? And this is actually a structure of people reporting to other people within organization. So every employee has somebody he reports to, and that person also has somebody else he reports to. As you can see, this structure could have different number of levels, and the number of these levels is unknown. So it could be actually any number and at any point. The structure currently presented on the screen is so-called unbalanced tree, which means that all branches of this tree have different lengths. As you probably see, the branch which is showing accountant has only one item, so it's only one person submitting directly to CEO, and nobody is submitting to him. But if you look at Department 2, you can see that within Department 2 there are groups, and there are people submitting to group manager. And within Department 1, there are no groups. There is just flat structure where each worker reports directly to manager of this department. So this is actually a pretty typical structure for a big corporation where they have variable number of levels. The implementation of this hierarchical structure with unknown number of levels in relational database is surprisingly very simple. What we need to do, we just need one single table for this, and we are currently showing our well-known table employee. And the only difference with previous employee table is the fact that we need to add just one more column to this table. And this column will be called manager ID. And obviously it will store ID of another employee who is manager of that employee. So this single column does everything. And unlike some other examples which we already looked at before, we don't even need to create another table. Just one single table can handle everything. And is it not just amazing? Look at the structure on the left. It looks like it's very far from table. It looks like it's very difficult to fit into tables, even into many tables. But in fact, just one single table can handle everything, which you can see on the left. In part 1 of this video series, I mentioned that graph structure also could be implemented in relational database. A graph structure is currently shown on this screen. It's somewhat similar to previous slide where we were looking at hierarchical structure, because that hierarchical was also graph. But graph could be more generic. And this is what we currently see. This graph doesn't have any hierarchy, so we cannot say that somebody is above somebody and somebody is below, like it was in management hierarchy for corporation, as we saw before. In a more general form, any node of the graph could be connected to any other node in any manner. So there could be links between all of them, or links could be absent as well. So how would we handle this more generic graph structure? For this, we actually just need 2 tables, and this is pretty simple. One table, we will call it node, and this will store our nodes of the graph and probably their names or any other information we want to store about node. And another table is called link. This table is obviously, according to its name, storing links between these nodes. And this table is logically connected to node table. It has 2 columns which are foreign keys, and these are from ID and to ID. So existence of the record in this table will mean that there is a link between a node with ID recorded in from ID and node recorded in to ID column. And also, I put some additional columns here. We can also put nature of this link. It's also very interesting information because it's very good representation of rich possibilities of graph. Nature could be reflecting what kind of link it is. And there could be so many different natures. It could be friendship. So this could be nature. So one node is friend of another in case they represent human person. It could be business relationship. It could be parent and child relationship. It could be doctor-patient relationship. It could be pet and pet owner relationship. So any kind of relationship could be represented by graph. And I also, just to illustrate another interesting opportunity, added column called strength. Strength means how strong this link is. For example, if nature of link is friendships, then how strong this friendship. Are they really close friend or just have some kind of acquaintance with each other? Or if it is business relationship, again, is it a strong business relationship or is it just some kind of slight relationship? So this essentially is implementation of graph structure, and I would say it's one of possible implementations. There are actually so many possible implementation could be suggested, but this is one of the simplest ones. And obviously this schema which I am currently showing is a little bit oversimplified because it assumes that all nodes are of the same nature. For example, they're all persons or they're all some kind of sales items. In real life, you may want to build graph on objects of different nature. It's actually also possible. It's not shown on this schema, but in this case, your link table will have additional fields. So it will not just have from ID and to ID, it will also describe what object it is. It will probably have column object from and object to. And this column will be storing table names. So in this case, it will be establishing a relationship between, for example, customer and his pet, or doctor and his patient, or doctor and his pet as well. You see, doctor also can have pet, so doctor can have patients from one side, and he can also own dog. So in this case, he will be owner of the pet. So it's another object and another kind of relationship. So you can model any kind of graph in relational database. Although it would be fair to say that graph database, and we already mentioned graph database many times in this video tutorials, is more suitable for this graph structure. Graph database is some kind of database which is specifically designed to handle graphs. And for example, it will be having some special language constructs, some special syntax for doing so-called traversal. Traversal is when you start from one node and go to all nodes which are connected, and next nodes which are connected, and next, and you handle as many levels as you need. And this is a kind of task which could be explained as friends of friends of friends. So, for example, somebody has friends, and we want to know friends of his friends and friends of those friends, and maybe we want to go something like 5 levels or more. So this kind of analysis could be useful in some research project. It's possibly useful in some kind of forensic investigation. So there is actually use of this traversal. And within graph database, you will have some built-in possibilities for this. However, traversal is also possible in relational database. It's a little bit more difficult. It requires some coding, but it's also possible. And on the next screen, I'm even going to present you some example of traversal which is made within SQL Server, which is obviously a relational database. So now let's see how can we implement this graph structure in a real database. As always, we start from the script which creates tables and script which inserts some data into these tables. As you can see, I'm creating table node and table link. And I'm inserting some names A, B, C, D into node table. I suppose that this node table will be storing some kind of human persons. I simply don't have place to put their long names here, so I shortcutted them as ABC. But you can imagine that there will be some real human names behind this ABC. And also I'm inserting links. These are mostly links from the previous graph shown on previous screen. I didn't put all links which were shown there, but I did put the most essential ones which I will be querying against. And also you can pay attention that we are currently having relationship of different nature. So some of these links are for relationship friend, means that the next person is the friend of previous person. Some of them are doctor, some of them are attorney. So we have all kinds of relationship. We have friendship, we have doctor-patient relationship, we have attorney-client relationship, and any relationship which we can imagine. Our first query would be to find all friends of person A. And as always, we start from template select from certain table, this time select from node. So we first need to select node for this person A. And in order to do this, we add where clause and we say where node name equal A. So this statement will return us our person we are finding friends for. And in order to find friends, we obviously need to do some joins. So we join it with link table. And how do we join with link table? We join on link from ID equal to our ID, because we want to link which is coming from the node we are talking about. So link from ID equal to node ID. That is not enough because it's only link, and we need to now to connect this link with node table. So we put join node, and here we illustrate one interesting case. As you can see, node table is mentioned twice within the same select statement, and this is perfectly fine. Select statement doesn't restrict you how many times you can use the same table, providing that you perform all correct joins. So our next copy of node table will have a little bit different name. I will say it friend node, because this is actually node for the friend. And I am putting this name because I need to distinguish the first name node from the second name node. If I have two nodes in one query, it will be a little bit confusing. So join as friend node, and this time on what we're joining? We're joining on link to ID. This is where we're pointing to. Now it will be equal to friend node ID. As you can see, once I rename it node table to friend node table, I can refer to this table as by new name, friend node. So in first row, table was called node. In second row, which is friends node, it's called friend node. So now I have all my joins together. And I need to add something to where clause, because I didn't want any kind of relationship. I only wanted relationship of type friend. So in addition to being name A, I need to put another condition here. I need link teacher be friend. And I type friend here. And let's say I'm not looking for any kind of friend, I'm looking for some kind of close friends. So I mean that strength of this friendship is at least 3. I put strengths in the scale, from 1 to 5. So 1 is weakest strength and 5 is the strongest strength. So I want them to be at least having strength 3. So I put strength more or equal 3. So all done, except that I need now decide what columns I will be selecting. Previously I used it as star, but I don't want to select everything. By the way, if I left it star like it was previously, then it will select columns from all 3 tables. 3 tables is link table and 2 copies of node table. But I only need information about friend. So I'm selecting from friend node. And I need name. And probably I want to show how strong is this friendship. So I go to link table and I grab strengths column from here. All done. Now I execute this query, and I find that friend of person A is actually person E, and strength of this friendship is 3. All done. This time we will look at way more complex example. This will be finding n level of friends, which is meaning that we not only finding immediate friends, but also we will find friends of these friends, then friends of those friends, and so on, until we go to a certain amount of levels. And levels will be n, which means it's variable. So we don't know how many levels in advance. If we knew how many levels, we can probably do it easier, but if we don't know, our task is a little bit more difficult. And this is typical so-called traversal task. It's actually a task which often executed on graphs. I already mentioned it at some point that graph database will have special statement, special syntax for this. In relational database, we don't have any special syntax for this, but we can still achieve this task by running some code, which is, among other things, is another opportunity for us to present you with new SQL statements. So let's go ahead and look how we will do this traversal. First of all, as you may already notice it, we will need to declare some variables. As most programming languages, SQL has variables. So not only it operates with tables, but also with variables stored in memory. And we introduce variables by this declare statement. And another requirement in SQL that each variable starts from this @ sign. This is simply SQL syntax for variables. We need 2 variables. One of them will be storing our maximum levels, so how many levels we have, and another will be our current level we are currently working with. And I just noticed that integer would be too big data type for this. Tiny integer will be sufficient, so I corrected to tiny integer. Now another variable, and it is another interesting SQL example, will be table variable. So this is special variable which stores table. But unlike our regular database table, this table is not preserved, so it only exists within our SQL script. So when we finish running our code, this table will disappear. But we will need it for some kind of temporary storage. It also starts from @ sign. We call this table friends. I declare it as a table. Now I need to put all columns which this temporary variable table will have. It will be ID of type integer. So declaration of this table is somehow similar to create table statement, except that this table is not created in database. It's only created within the scope of our code, which we are currently running. So ID integer, name will be var 50 as our all names are declared in node table. And I also want to store level. It will be tiny integer. I want to know at which level this friend which we found was. So we are done with our declaration. We need to assign initial values to our variables. So our current level will start from 1. And our maximum level in this example will be 3. So the code will work with any number of levels. And you also see how do we assign variable values in SQL. We use set statement for this purpose. Another initial action we need to perform, we want to put our primary person, the person we are finding friends for, into our friends table. This will be our starting point, and we will assign level 0 to this person, meaning that it's not actually a friend, it's a person itself we are looking friends for. And we'll be running insert statement for this. But this time, the format of insert statement will be different. Previously, we used it very often insert statement with values clause. This statement was inserting particular data into table. Now I will use insert statement in a different form, and this is actually probably most frequent form of this statement, where this statement is immediately followed with select statement. And what the statement will be inserting is actually records which were produced by following select statement. So let me show how this all works. So insert friends. Write our column names will be inserted into ID, name, and level. And then we run select statement, which will be actually giving us results for this insert. And we want temporarily put star, because I just need to write statement. We want to select from node where name equal to A. This is our first person we are looking friends for. Name equal to A. And now I can go back and put actually column names here. ID, name, and now level is not coming from table, it's just 0, because we are inserting first record with level 0. So we're currently done with our initialization part. We already done with level 0, and now we need to go through all levels starting from 1 and up to max levels. How do we normally run through many iterations? We use cycle for this, and cycle statement in SQL is while. Put while statement. We run it while our current level is less or equal to our next level. Then we put begin and end. This will be our kind of brackets for our cycle. This will be showing body of our cycle. And what we need to do inside our cycle, we need actually to run another insert statement into friends table, but this time we will be inserting friends, not the person itself. So I will copy the first portion from here. It has the same syntax. Insert friends table and column names. And now I need to put select statement, which will be giving me these friends. I temporarily put star here. I will finish it later. What we inserting from? First of all, we need to take records from our friends table, which we inserted before, because we are looking next level of friends, so we need to know previous friends. So I'm saying from friends where level, I need previous level, I need level previous to one I'm currently working with, where level equal to current level minus 1. This way I refer to previous level. Then we need to join this friends table with link table. Join link. We're now looking at all links which are initiating at our existing friend records. So join link on link from ID equal to friends ID. And I need to put this square bracket, just SQL syntax requirement when I'm using table variables. Friends ID. Now, these links point to our next level of friends, which are coming from node table. So I'm joining this node table on, and this time link will give me 2ID. And 2ID will be equal to node ID. So it's almost all done with joins. And now I realize that in our where clause we need to put another restriction. We already told what level we need, but also we need to put restriction on link table, because we're only interested in friend relationship. So we need to say that link nature equal to friend. We don't want that this code pick up some kind of doctor-patient or attorney relationship. Only nature equal to friend. So express this restriction by saying this phrase link nature equal to friend. So far we did everything, and what is left is to put our column names. Our column names are coming from node table, because this is where we're getting friends from. So we say node ID node ID. We also take in node name. And we need to put level. What level we need to put? We need to put our current level. This is level we're currently working with. Our current level is stored in variable. It's not stored in table. So we are almost all done with our cycle, except that we need to go to our next iteration. This form, as you currently see, it will run forever. So we will obviously need to advance to next current level. We can do it in using different kind of syntax. We can just say current level equal current level plus 1. It will increment it by 1. Or we can use actually a shortcut which exists in SQL Server for this. This is shorter form of this statement. We can write it like this. We can say plus equal 1. So in this form, this statement does exactly what we wanted. It increments this variable current level by 1. So we are currently done with our cycle, and what is only left is to return results, what we just produced. And if you remember, our results are in friends table. So we are saying select ID name level from friends. And apparently want to order by these results by level. First one person itself, and then all levels of friends we found. So I'm briefly reviewing this code. It looks like everything is correct so far. So let's go ahead and execute this code. I click on execute button, and I have perfectly delivered results. As you can see, our first person A came at level 0. This is our original point. Then this person had two friends. This person had one friend, and it was person E, and it's level 1. And person E had another friend, and it was person P, and level is 2 at this time. And P had two friends, and these friends were persons Q and F, and level is 3. So we just completed our task. I have illustrated that we can do database traversal in relational database. I will show you this code again if you want to look at this. You may notice that we needed to write some code which was not pretty straightforward, but it was not difficult either. And if you wrote it once, you can reuse it, so it's not really that difficult. And also note about kind of code I wrote. This is one possible implementation of this traversal. There could be so many different approaches to this. There could be one elegant approach with using recursive functions. There could be another interesting approach with using so-called CTE, which stands for Common Table Expressions. There are actually many implementations of this code. I'm not going through all of them because obviously this is not teaching material on SQL as a language. I only needed to use SQL to illustrate some kind of database design examples. And there is always a question, what is better? Is it better to use all this code and use relational database, or is it better to use graph database, which is specifically designed for this graph traversal? The answer to this depends on how big is your graph portion in your database. If you're intensively working with graphs, means that almost all your data are in graph form, maybe graph database would be better for this project. If only some small portion of data is in graph form, but most of the data you have are in tabular format, you can still use relational. It will be working easily with all tables, and your graph portion could be implemented by code like the one which I just presented. This is end of part 5 of this video series on relational databases, informal introduction. In this part, we learned how to fit various hierarchical and graph structures into database tables. At this point, we didn't learn yet how to fit totally unstructured data into tables, which is also possible. And next parts, we'll be talking about this.